This video is about Green's theorem, which allows us to relate line integrals over closed curves to equivalent double integrals over the region inside that closed curve. In the video, we will review line integrals of vector fields and flux integrals of vector fields. Then we will review and introduce some important terminology that's related to the requirements of Green's theorem. And then we'll state Green's theorem in its tangential and normal forms and interpret Green's theorem in the case when F represents the velocity of a fluid. And lastly, we'll do an example, maybe two examples depending on time. The proof is also very important, but we aren't going to do that in this video. I will make another video for that for those people who are interested. So this video is about Green's theorem, and specifically it's about what it says, what Green's theorem means, and how to apply it. So let's start by reviewing line integrals of vector fields. So let's say we've got a vector field in the plane. F is given by components m of xy and n of xy. So it assigns a vector to every point in its domain, and its domain is a subset of the xy plane, and it might look something like this. And then let's say you also have a curve C given by a piecewise smooth parameterization R of t with components x of t and y of t. And then let's say we start over here at t equals a, and then as t increases, we move along our curve, and then at t equals b, we end up over here. Well, the line integral of f over c is written this way, and we introduced this initially with the line integral over c of f dotted with t hat, where that's the unit tangent vector, times ds, that's a tiny length along the curve. And we said that integral is equal to this integral. That's the line integral over c of f dotted with dr. And r is a position vector. So this is a change in position per unit time times a tiny change in time. So then if we want to evaluate these, we need some variable to tie everything together. I've got a lot of variables here. I've got f representing my field. It depends on position x and y. I've got a c representing the curve itself, but that's given by r of t. Now r has components x of t and y of t, and we know that t goes from a to b. So we've got a lot of different letters here. But the one variable that ties everything together is t. And I think this is easiest to see if you think of this as representing work. So remember, whenever we were interpreting this line integral as work, this is our first of two applications of this. And it's interpreted as work whenever F is a force. It's a force acting at a certain location, xy, in the xy plane. So we can see that this integral should represent work if we interpret all of these little pieces here. Because remember what work is. If I've got a force acting to move some object through some displacement, work is defined to be the dot product of force with displacement. Or if you prefer, you can think of it as the force in the direction of motion times the distance traveled in that direction. Well, if I remember it that way, and then I remember what all these symbols means, it actually makes a lot of sense. So just to interpret this, let's take a part of the curve, maybe this part of the curve here, and zoom in. So if I'm zooming in, my curve might look something like this. So I'm going this way along the curve. If I'm at this location, the unit tangent points in the direction that I'm going. So it points this way. And the unit normal that we studied previously always points in the direction that we're turning. So the unit normal goes this way. Now, for the most part in this chapter, we're not going to be focused on the inward unit normal. We're going to focus on the outward unit normal. This is the opposite normal, the normal that we ignored when we were studying vector valued functions. So I'm going to call the normal that we talked about before n star. because we're going to ignore it from now on, but that's the inward unit normal. The outward unit normal points the other way. But if we're on our curve, and this is our unit tangent, if we're at this location, if we are a particle traveling along this curve and we're at this location and F represents a force, well, the force that I'm experiencing while I'm at this location is this force right here. And if I want the work done by this force and moving me through a tiny displacement along this curve, I have to find the part of the force that is acting in the direction that I'm going, and then multiply by the distance that I travel through as I go in that direction while I'm experiencing that force. Well, the part of the force that's acting in the direction that I'm going is the projection of F onto T hat. And the projection of F onto T hat is the magnitude, or the magnitude of the projection of F onto T hat is the absolute value of the dot product of F with T hat divided by the length of T hat. But remember, T hat's a unit vector, so dividing by the length of T hat is dividing by 1. So really the length of that projection, or the magnitude of the force acting in the direction that I'm going, is given by this. Now, if the force is actually acting a little bit in the direction that I'm going, so that the component of the force parallel to the direction that I'm going points in the same direction, well, then this dot product is positive and I don't need the absolute value. Now, if that force were pulling me backwards and I was trying to go forwards, but it was pulling me backwards a little bit because the force is over here and the part of the force in the direction or parallel to the direction that I'm going was pulling me this way, well, then that dot product would be negative. So this F dot T without the absolute value is basically the signed projection of the force onto the unit tangent. It's the magnitude of the force in the direction that I'm going, and it's positive if it's acting in the same direction. It's negative if it's acting in the opposite direction. So I take this force, and then I multiply it by that tiny distance. Force in the direction of motion times a tiny distance is work, and then we add all of those together to get the line integral of F over C. So then we'll say the total work done by the force on the object as the object travels along C is given by this integral. And we showed earlier that this is equal to this. Just using our definition of ds and our definition of t hat. Okay, now you say that's a lot, but now I know it represents work. How do you actually evaluate that? Well, the one variable that ties all the variables together is t. When I'm on this curve, x is given by x of t and y is given by y of t. So the field that I'm experiencing as I travel along the curve is f evaluated at x of t and y evaluated at y of t. So now I've got my field as a function of time. It wasn't originally a function of time. It was originally just a function of position in the xy plane. But as I travel along the curve, I'm experiencing different fields. I'm experiencing different forces. So this is the force that I would experience if I traveled along this curve and I was at this location at a particular time. So if I take that force and I dot it with r prime of t, that's going to give me a scalar function of t, and then I just evaluate it the same way I would in Calculus 1. This is just a scalar function of t, and I integrate from a to b, and that's giving me the line integral of f over c. So if F is the velocity field of a fluid, that represents work. Now, or I said the absolute opposite thing. I was getting ahead of myself. If F represents a force field, so a force acting at different locations, this represents work. This is the other thing. If F represents the velocity of a fluid, then we interpret it differently. Same vector, same projection, but we're interpreting this differently. If this is the velocity of some fluid, if I take the projection of F onto T hat, that is, well, that's the part of the velocity that's acting in the direction that the curve is being traced out as T increases. So we say that this, which is equivalent to this, represents the flow of that fluid along C. It's a measure of how much of that fluid is flowing in the direction that we're going. Now, again, sometimes that is going to be a negative dot product, sometimes it's going to be a positive dot product, but we add them all together and we get some number, and that represents flow. Now, if that curve happens to be a closed curve, we call that circulation. And if the curve C is closed, we put a little circle around our integral sign. So that's the circulation around C in that case. But this is what we get if F is the velocity field of the fluid. We say, how much is that field sort of aligning with that curve, going in the same direction that that curve is flowing, or that curve is going? Well, that's flow. Or how much is that fluid flowing around C? And then we call that the circulation of the fluid flow around C. Okay, so that's a line integral of F over C. Now, I'd like to introduce or review some important terminology. We say that a curve C is simple if it does not cross itself. We'll say it's simple on the interval from A to B if it does not cross itself for T between A and B, not including A and B. Oops. So here is a simple curve. That's simple. This is also simple. Here's a curve that's not simple. Because it crosses itself right there. Oops, there's a closed curve that's not simple. And a closed curve is just a curve where x of A, y of A, and x of B, y of B are the same. So we start and stop at the same place. So x of A, y of A, that's just a point in the plane. And x of B, y of B is a point in the plane. If we happen to start and stop at the same location, that is called a closed curve. So this is simple and closed. This is simple and it's not closed. This is not simple and it's not closed. And we could pick any point here and we could call that our starting and stopping point. So we'll say that that's not simple, but it's closed. Okay. Now, a simply connected region R is a region that has this property. Every simple closed curve in R encloses only points in R. So here's a simply connected region. If I have a curve in R and it stays entirely in R, it's never going to accidentally grab some points that aren't in R. So this is simply connected. And then here's a region that's not simply connected. Because I can draw a curve that lies entirely in R as a simple closed curve, and it does have some points inside that simple closed curve that aren't in R. This is not simply connected. Now I'm going to state the first form of Green's theorem. It's called tangential form. And it's related to this line integral of f over c. Now it has some qualifiers, some requirements. The farther we go in math, the more qualifiers we seem to have. We say let R be a simply connected region. And we are in the xy plane, so it's in R2. With a piecewise smooth boundary. C, and that C has to be oriented counterclockwise. If it's oriented, I wrote clockwise, counterclockwise. If it's oriented clockwise, just multiply by -1, you get the right answer. And let F be a field in the plane with components M and N, where M and N have continuous first partial derivatives in an open region containing R. If you're wondering, why does it have to be open? We just mean that M and M have to have continuous first partial derivatives on R, on the interior of R, and on the boundary of R. In order for it to have, in order for M and N to have continuous first partial derivatives on the boundary, they have to have continuous first partial derivatives in an open region containing R. So let's draw a picture. Maybe this is the curve C. The interior of this is R. This is our curve C, and it's oriented counterclockwise. And F is a field with components M and N. And M and N have continuous first partials on an open region containing R. So those first partial derivatives are well defined on that boundary and on the interior of R. And I'm just putting that there just to remind us why that little dotted line is there, dotted curve is there. If all of this is true, then we get this double integral. The line integral of f over c. So this is the integral that represents circulation if f is the velocity of some fluid. It represents work if f is a force acting on a particle that's traveling along this curve. It turns out that this is equal to this over here, the double integral over r of the partial of n with respect to x minus the partial of m with respect to y. Now let's focus on that interpretation as circulation. So if f represents the velocity of some fluid, then this represents the circulation of that fluid around C. And our curve C is closed, so we could put a little circle like that. Well, that's equal to this over here. Now, if you're wondering what this is, we're going to think of this a little bit differently. Now, this is actually related to curl. It doesn't look like it's related to curl, and you might be saying to yourself, how can you even have curl? We're in the plane. Well, you would have to think of this, this field and this region R in the plane as existing as a plane in three-dimensional space. So we've still got the x-axis here, the y-axis here, z-axis is pointing up. So we've got our z-axis pointing in the direction of my Sharpie, pointing straight up at you. Well, this is the curl of f dotted with k hat. So this is the signed projection of the curl of f in the direction of, in the z direction, basically. And let's prove that. So let's say we've got our field f, it has components m and n, but now we want to think of it as being in three-dimensional space. So we've got this new version of f. If it lives in 3 dimensions, it has components m, n, and 0. If I take the curl of f, and I'm going to write it like that, just to remind myself that it's a vector, that's the del operator crossed with our field f. We get this. First, we cross out the row and column containing I hat, and we get the partial of 0 with respect to y, which is 0, minus the partial of n with respect to z. But remember, m and n only depend on x and y, so this is going to be 0 minus 0, so we just get 0. Minus, cross out the row and column containing k or j hat, and you have to multiply by -1. Then you have the partial of 0 with respect to x, which is 0, minus the partial of m with respect to z, but it doesn't depend on z, so we get 0 there. Then finally, we cross out the row and column containing k hat, and we get something that's non-zero. We get the partial of n with respect to x, minus the partial of m with respect to y. So our curl vector, it's the cross product of this guy with the del operator, gives us this. Notice that that curl vector lies entirely in the z direction. You're saying, well, what does that mean? Well, it makes sense because our plane or our curve is down here. Somehow when we have that, take that cross product, the entire cross product ends up pointing up or down. It's not going to have any components in the x or y direction because the curve or the field lies entirely in the xy plane. So we get this. Now, if I take this vector and I dot it with k hat, So that's 0, 0, partial of n with respect to x minus partial of m with respect to y, dotted with 0, 0, 1. We just get that z component. So this is the part of the curl in the direction of z, but it's actually sort of the entire curl if I'm just focused on it as a scalar. It's just the curl, whether the curl, this component is positive or negative. If our field is in the plane, the curl only has one component, either it's in the z direction only. If this number is positive, the curl points up. If that number is negative, the curl points down. So this is, it's really just the magnitude of the curl. It's the signed magnitude of the curl. Okay. So now let's think about what this says. This says the circulation around C. So F is the velocity field of some fluid, and we're going around C. And we're figuring out how much of that fluid is moving with C. It's just moving this way in a counterclockwise direction. If it moves in the same direction as C, in general, that dot product is going to be positive, and we'll get a positive number. So if it has a tendency to rotate this way in the counterclockwise direction, we're going to get a positive circulation. If in general, when you add them all up, it has a tendency to rotate in this direction, we'll get a negative answer. Well, this is saying that rather than taking the circulation around C, we could do something else instead. We could find the signed magnitude of the curl of F. And remember what the curl represents. We'll review that in just a second. We'll take that signed magnitude of the curl of F and then multiply it by a tiny area piece, and then add them all together, and that's going to give us the circulation around C. Okay, so in order to really understand this, I really need to understand what curl is, or I need to remember what curl is. So let's review briefly what curl is. When we talked about curl, we said informally, or I think I used the word intuitively, but I've been using those words interchangeably. Maybe I shouldn't. Maybe I should be more, check my accuracy on that. Informally, we said that the curl of F is a measure of how much the field swirls about a point. So if we saw fluid that looked like this, if that's what our field looked like, we would say, yeah, there's a curl there. If we saw something that looked like that, saying there's no indication of anything curling. So this is 0 curl, and this is non-zero curl. But really, I'm talking about magnitude, aren't I? So I'm saying that there is some curl there. Now, since it's going in the positive direction, or since it's going in the counterclockwise direction, the magnitude of this number would be positive. Now, if these guys were going the other way, so in the clockwise direction, this is also a non-zero curl, but it's going in the opposite direction from this direction. We had to choose a direction. We had to say, well, this is going to represent positive from now on, and the other way is negative. Because of sign conventions, we say that's positive, and this is negative. Okay, so this curl, it's a vector. It's a measure of how much the fluid swirls around a point. If that curl is positive, the vector is actually pointing up like this. It's pointing in the direction of k hat if our hands or our fingers sort of go with the fluid flow. So it points this way. So, and then we're going to call that positive, and it's counterclockwise relative to this axis, the positive z-axis or k hat. Now, if I use the right hand rule and I go this way and I wrap my fingers around in the same direction that my field is going, my thumb is going into the page. So the curl is actually going to be this number times negative k hat. And of course there, the direction doesn't matter because there's not a lot going on with the zero vector. Okay. Okay, so now what does this mean? So this is saying, go to every single point in the region R and find the curl. And then take that curl and multiply it by the area. When you do, we have this curl times area, and we add all of those pieces together. So I've got curl at this point, and curl at this point, and curl at this point. And it's a measure of how much the fluid is rotating at each of those points, at each of those locations. Well, it turns out you're going to get exactly the same answer here that you get from just looking at the circulation around the outside. So the circulation around the outside tells us how much that fluid is flowing along this curve in this direction. Well, this says, instead of doing that, why don't you find the curl at every point and then multiply it by a tiny area and then add all of those together. And that's going to give you exactly the same answer as if we found the circulation around the outside. It's like you're taking the circulation at each of these individual points and then you're summing them. That's the idea. So this informal definition of curl that we had earlier can be adjusted. We're saying curl is a measure of how much the fluid swirls at a point. Or I really should say the magnitude of that is a measure of how much it swirls at a point. The direction, if our field is in the plane, is going to be determined by whether we're going counterclockwise, we'll call that positive, or clockwise, we'll call that negative. But according to this, what this is telling me is that this curl times a tiny area is giving me circulation sort of about a certain location, about a point. So curl times area is circulation. So curl is, in a limiting sense, it's circulation per unit area. So I guess this is just another informal definition, but it's at least a slightly more formal than the last one. It's a measure of how swirly something is. So we can think of curl as circulation per unit area or circulation density. It's like circulation about a point. So we take our circulation per unit area and we multiply by area and we add those all together, and that's going to give us circulation around the outside. And I think that makes sense. Okay, that's tangential form of Green's theorem. I think I promised you that we would do tangential and normal form in the same video, but I think that's a little too much. Let's just focus on tangential form. We'll do one example, maybe two examples, and then in the next video we'll talk about normal form. So let's say we're given this field. And we're given a curve C, and C looks like this. It's given by y equals x on one boundary, and y equals x squared minus x on another boundary. So it kind of looks like this. So this is our curve C. And the region inside is called R. Someone may ask you to, let's say this is our force. Find the work done by F on a particle moving counterclockwise around the path C. Okay, now let's check our conditions. Where's our theorem? Got all of these conditions. Is R a simply connected region in the xy plane? Oh, sure. Any simple closed curve in R is going to stay entirely in R, so we're good there. And it has a piecewise smooth boundary C. Sure, that's smooth and that's smooth. Oriented counterclockwise. If they didn't give us the orientation, we could draw in an orientation. I already automatically drew it in as counterclockwise. Cool. Now F has to be a field with components M and N have to have continuous first partial derivatives in an open region containing R. Oh, sure. M and N are polynomial functions, so their first partial derivatives are going to be continuous in the entire xy plane, so we'll have no problem with those being continuous on an open region containing R. Okay, well then according to Green's theorem, this integral is equal to this integral. Now this is the interpretation if F is the velocity of some fluid, but that's not what we have here. We're asked to find work. But remember, work is this, given by that same line integral. According to Green's theorem, this is equal to the partial of n with respect to x minus the partial of m with respect to y. And this line integral over C is equal to the double integral of this function over the region R. Since all the conditions check out, we can just apply the theorem. So I'll state my theorem. Well, first we had to state the, check the conditions of Green's theorem. And we did. And then we stated the theorem. And then the next thing we want to do is compute those two partial derivatives. Now notice that if the field is conservative, the partial of m with respect to y and the partial of n with respect to x will be equal to each other. So when we subtract these, we'll get 0. And we already actually knew that. If the field is conservative and we have a closed curve C, we should get 0 as long as the conditions of that theorem hold. So yeah, if you forget to check that the field is conservative, or if you check that whether or not the field is conservative by computing these two partials and they happen not to be, but you have a closed curve, C. Then rather than using the fundamental theorem of line integrals, you can use Green's theorem instead. So we're just going to compute those two partials, and then we'll state the bounds for R, and then we'll integrate. So we want the partial of m with respect to y. X cubed is constant with respect to y. The derivative of y squared with respect to y is 2y. And we want the partial of n with respect to x. Well, the 1/4 is constant. The y is constant. The derivative of x to the 4th with respect to x is 4x cubed. The 4 is reduced, and you just get x cubed y. They're not equal, so the field isn't conservative, but if I subtract them, they actually subtract pretty nicely. It's just this minus that. So we are substituting into our integrand now. The line integral over the boundary is equal to the double integral over R of the partial of n with respect to x, which was x cubed y, minus the partial of m with respect to y, which is 2x cubed y. So we get negative x cubed y. We just have to integrate this simple polynomial function over the region R. That's pretty easy. All right, so we've got our new integrand. Now we just need bounds for R, and then we'll evaluate the integral. Okay, to find bounds for R, I notice that if I draw my rectangles this way, the top function is x the whole time, and the bottom function is that x squared minus x. So this is going to work out just fine. It makes sense to let y go from a function to a function and let x go from a constant to a constant. So y starts at this bottom function and goes to that top function. And then x goes from a constant to a constant. It goes from 0 to whatever that value is over there. To figure out that value, we'll just set the y on this curve equal to the y on that curve and solve for x. So I'm calling those y1 and y2 for these two separate curves. Subtract x from both sides. Factor out the x. And we see either x equals 0 or x equals 2. Makes sense? It's consistent with our picture. Okay, so y is going from a function to a function, and x is going from a constant to a constant. So that means we have to integrate with respect to y first. So we've got to, after we find our bounds for R, set up the integral. And then we evaluate. So y goes from x squared minus x to x, and x goes from 0 to 2. All right, we're here. So I'm really ignoring that outermost integral first, focused right here inside. X cubed's a constant with respect to y, so we bring that down, and then we anti-differentiate y to the first. So we add 1 to the exponent and divide by the new exponent. Then we substitute in y equals x squared minus x and y equals x, and we subtract. Evaluate at the upper bound and the lower bound, and then subtract. I have 1/2 x cubed, so I'll factor that out. And then at the upper bound, we replace x or y with x, so we'll have x squared there. And then we replace y with x squared minus x. So I have x squared minus x quantity squared. You can write this twice in FOIL. We're just doing a little algebra. First times first is x to the 4th. Outer times outer is negative x cubed. Inner times inner is just like it. Last times last is positive x squared. After you multiply those together, don't forget to multiply the whole thing by that -1. So we distribute the negative. The x squareds reduce. And now if we distribute this 1/2 x cubed to everything, we have a -1/2. X cubed times x to the 4th is x to the 7th. And then we have a 1/2 times 2 is a +1. X cubed times x cubed is x to the 6th. We've got a negative outside. I'll bring that inside just because I want that coefficient to be positive. Okay, now let's just use the power rule. Bring the 1/2 down, add 1 to the exponent, and divide by the new exponent. Add 1 to the exponent and divide by the new exponent. Substitute in 0 and 2 and subtract. I have 1/16 times 2 to the 8th minus 2 to the 7th over 7 minus 0. And 16 is actually 2 to the 4th, so that will reduce to 2 to the 4th. So we've got 16 minus 2 to the 7th over 7. And I think I'll use a calculator for the arithmetic. Oops. Okay, so we get -16 over 7. Okay, so that is the value of our line integral. Let's go back. Let's find the work done by the field on the particle moving counterclockwise around C. Well, depending on what these dimensions are, looks like the work was -16 over 7. So I guess the field is not doing work on the particle. The particle must be doing work on the surroundings instead. But as we're going around this curve, these dot products end up being negative more often than they're positive, or at least their magnitudes end up adding to a negative number. So we get a negative number here, and that's the same as this over here. Now, I want you to remember and think about how much work this just saved you. If I wanted to evaluate this the traditional way, I would have to come up with a piecewise smooth parameterization for this. So maybe I would let x equal t and y equal t squared minus t on the interval from t equals 0 to t equals 2. And then from t equals 2 to t equals 4, maybe I would let y equal 4 minus t, and then, or 2 minus t, and then let x equal the same value. I think that would work. So we end up with a piecewise smooth parameterization of this. Then we have to write our field in terms of x of t and y of t for this curve and this curve. We'd have to compute r prime for each of those curves, take dot products, and evaluate an integral from 0 to 2 and evaluate an integral from 2 to 4. Add those together, and you're going to get -16/7. Or, and this is the beauty of Green's theorem, you could say, well, that's a closed curve, and my region R is simply connected, and my curve C is being traversed in the counterclockwise direction, and the partials of M and N are continuous on an open region containing R. So rather than doing all of that, rather than evaluating a line integral here and a line integral here and adding them together, I can say, let's just do this instead. Compute those two partials, subtract, state the bounds for the region R, and integrate. I think it's pretty nice. It's very nice. Let's do one more example of this. And then in the next video, we'll look at the normal form of Green's theorem. So let's say our field is a 2 arctangent of y over x and natural log of x squared plus y squared this time. And let's say that f represents the velocity of some fluid. In a region in the xy plane where both of these are well defined. And let's say the curve C is given by this equation. We've got x minus 4 squared over 4 plus y minus 4 squared is equal to 1. And you're asked to maybe find the circulation of f. Or find the circulation of the fluid over C. Well, let's make sure that the conditions of Green's theorem are satisfied. Notice that the curve C is given by the equation of an ellipse, and it's an ellipse with center 4, 4. A squared is 4 and B squared is 1. So we're going to go over here to x equals 4 and y equals 4. That's our center. And because a squared is 4 and a is under the x, we're going to go plus and minus 2 units in the x direction from the center. So we're going to go back to 2 and then forward to 6. Meanwhile, we've got a b squared under the y term. B squared is 1, so we go plus and minus 1 unit in the y direction from the center. So there's our curve C. And we want the circulation of the fluid along C. This is the region R. I drew, or I oriented the curve C in a counterclockwise direction so that Green's theorem would apply. Now, first I want to state what they're asking me for. Well, circulation is a line integral of f dotted with dr. So we want the value of this. It's a measure of how much that fluid is flowing around this curve. And that corresponds to this, according to Green's theorem, provided that certain conditions hold. So we need to check and make sure those conditions hold. So we need to verify that the conditions of Green's theorem are satisfied. What do we need? We need a simply connected region R, and that is simply connected. Do we have a piecewise smooth boundary C? Actually, yes, it's smooth the whole time. Oriented counterclockwise? Sure. And that was our choice. And then what's the last thing we need to check? Ooh, this one's a little bit more challenging this time. Here's my M and there's my N. My field has to have component functions M and N that have continuous first partials, or continuous first partial derivatives, in an open region containing R. Okay, so M is this function. Let's find its first partials with respect to x and y. The derivative of M with respect to x, treating y as a constant, is 2 times the derivative of arctangent of a function. The derivative of arctangent of a function is 1 over 1 plus that function squared times the derivative of the inside with respect to x, treating y as a constant. So this is the same as the derivative with respect to x of a constant times x to the negative 1. So this ends up being a constant times a negative x to the negative 2. So we end up with 2 over 1 plus, oops, that should be squared, y squared over x squared times this, and that is the same as a negative y over x squared. When I distribute, I get negative 2y over x squared plus y squared. All right, so question is this continuous in an open region containing R? Well, the only problem I'm going to have is at 0, 0, and we're nowhere near 0, 0. So this one's continuous, we're good. Now let's find the partial of M with respect to Y. So we bring our 2 down, and then we take the derivative of the arctangent of y over x with respect to y. So that's 1 over 1 plus the inside function squared. The inside function is y over x. And then we take the derivative, we multiply by the derivative of y over x with respect to x, treating x as a constant. Well, you can factor out that 1 over x. That's really just a constant times y. The derivative of a constant times y is just the constant. So what we get here is 2 over 1 plus, if I'm squaring a fraction, I can square the numerator and denominator separately, times this, which is 1 over x. I'd really like to clear that complex fraction, so I'm going to multiply by another 1 over, or by another x over x. Because that's just multiplying by 1, it doesn't change the value of the fraction. But now I've got an x squared that I can distribute through here, and it'll simplify nicely. So in the numerator, I get 2x. In the denominator, I've got x squared times 1 plus y squared. And again, the only problem we have is when x squared plus y squared is 0, and that is nowhere near our region R, so we're good. We've got M has continuous first partials in an open region containing R. It's actually has continuous first partials in all of the regions in the xy plane that do not contain the origin. Okay, and we're actually going to need that later for our integrand, so that's good. Now we need to take the partial of n with respect to x, and n was natural log of x squared plus y squared. This also requires the chain rule. We've got an inside function there. The derivative of log of a function is 1 over the function. And then we multiply by the derivative of the inside with respect to x, treating y as a constant. Really? Okay. We get 2x over x squared plus y squared. So that's continuous. And I'm going to stop this pretty quickly. With respect to y, we do the same thing. 1 over the inside function times the derivative of the inside with respect to y, which is 2y. This is continuous on an open region containing R as well. Okay. So this is satisfied. So Green's theorem applies. But you know what else is satisfied? If this is M and that's N, the field is conservative. So let's check it out. Let's say we didn't notice that, or I didn't. Let's say you didn't notice that. You verified that the conditions of Green's theorem were satisfied, and you said, okay. Then we substitute and we evaluate the integral. So according to Green's theorem, this integral is equal to this integral. But watch this. The partial of n with respect to x is 2x over x squared plus y squared. And the partial of m with respect to y is 2x over x squared plus y squared. Now that may not have been obvious if you hadn't, or if I hadn't simplified that first to clear my complex fractions. But after simplification, we see those are equal to each other. If these are equal, that means the field is conservative. And of course, that is 0. So what does that mean? Does that mean there's no fluid moving with this curve at all? No, that's not what it means. It means that every time that the fluid was moving with the curve, well, there was also some time or some part where the fluid was moving in the opposite direction of the curve. So the curve is going this way, and then the dot products were negative, maybe on one side, or for some parts. Dot products are going to be negative sometimes, positive sometimes, and then when you added them all together, because the field was conservative, we got 0. Okay. So let's briefly review Green's theorem. Here's the theorem in tangential form. So if we have a simply connected region in R2, so all of the simple closed curves in R stay in R. They don't enclose any points that aren't in R. and we do in this picture. And R has a piecewise smooth boundary, so no sharp corners. Well, you can have a finite number of sharp corners. That would make it piecewise smooth. And it's oriented counterclockwise, so we do that. If that's true, and the field has components M and N have continuous first partial derivatives in an open region containing R, so that means on R, on the boundary of R, and like really close to that boundary. Then the line integral over C, and C is a closed curve, is equal to the double integral of this. And we said if F represents the velocity of a fluid, what that means is the circulation around the boundary is equal to this signed magnitude of the curl of F times dA, the sum of all of that, of all of those pieces. So we go to every single point in the region R, and we calculate the curl, and we calculate the curl, and we calculate the curl, and we look at its magnitude, and if the curl is pointing up, we count that as that magnitude as positive. If the curl is pointing down, we count that magnitude as negative. We add all of those up after multiplying by a tiny area piece. If we do that, that's giving us the circulation around the boundary. So now we can think of curl as a circulation per unit area. Or in this case, yes, it's circulation per unit area because we're in the plane. In practice, how do we do this? We check the conditions of Green's theorem. So we make sure those first partials are continuous. We make sure we've got a simply connected region R. We make sure we've got a piecewise smooth boundary oriented counterclockwise. Then we just compute a couple of partials, substitute, and then we find the appropriate bounds for R. So we let y go from a function to a function and x go from a constant to a constant, or the other way. Either one would be fine. And then you set up the double integral and evaluate that rather than evaluating this. Now this really isn't too bad. The other one's not bad either, it's just long, right? Remember what you would have had to have done otherwise. You'd have to come up with a piecewise smooth representation for this and this, right? Two integrals, and so you'd have to have the field in terms of t, r in terms of t, compute a dot product of the field with r prime, evaluate an integral here and evaluate an integral here. Or if Green's theorem is satisfied, all you have to do is compute a couple of partials and then integrate over the region, which I think is pretty nice and pretty simple. So we started this video here, and we reviewed line integrals, and we stated the tangential form of Green's theorem and interpreted it when F was the velocity of some fluid, and then we did a couple of examples. In the next video, we're going to look at flux integrals and the equivalent normal form of Green's theorem, and then we'll interpret those and do some examples as well.